Hello everyone, this is Prem Kumar Chinaraj, Mechanical Technology Specialist from Wood. In today's presentation, we are going to look into some of the techniques that can be implemented in coke drum lifecycle management. Most of us know that coke drums are equipment that undergo severe thermal cyclic service. Temperature extremes along with thermal gradients during cooking and water quench are one of the primary contributors to fatigue damage of the drum. Thermal bowing, in other words banana expansion, is another phenomenon frequently seen in coke drums. It is caused by channeling of water during quench, which results in uneven cooling of the drum in circumferential direction. This lateral displacement of the drum need to be calculated to provide enough clearance to the structure and determine the increase in piping and flange loads. Another important factor to consider is vibration-induced fatigue that causes cracks both in drums and overhead piping. Therefore, dynamic analysis is necessary to determine the location of pipe supports to reduce vibration, thereby increasing the natural frequency of the system. In this slide, we will be looking at different forms of damages encountered in coke drums. Bulges are typically seen at the shell, especially in drums built with carbon half moly. This is caused by ratcheting, which results in cyclic straining of the drum, thereby inducing fatigue cracks. At the same time, it also causes cyclic incremental growth of drum, leading to permanent bulges or distortions. The cause of bulging is primarily attributed to high flow rate during operation, which in turn causes high temperature differential in the shell. Cracks. Critical areas of the coke drum that experience fatigue cracks are skirt attachment welds, keyholes, nodules, circumferential weld seams, and bulges. We will be discussing more about cracks in skirt welds and keyholes in the upcoming slides. Anchor bolt failures. These are primarily caused by banana expansion and vibration of coke drum during operation. Tilting of drums are caused by deterioration of foundation, corrosion, and cracks at base plate. This permanent tilt will result in higher loads on connected overhead piping and flanges, thereby causing leakage. To avoid leakage at the bottom unheading flange, thick flange needs to be designed to resist the thermal transients with improved bolt tensioning practices. Corrosion on the IDF drum is mainly caused by sludge in the feed and water during quench. In some cases, during coke cutting process, the hot coke slides down the cone, resulting in erosion followed by corrosion. In wood, our goal is to design fatigue-resistant coke drums that meet minimum of 7,000 life cycles. We also coordinate with our fabricators to make sure they meet our stringent requirements provided in our specification to achieve the intended fatigue life. After startup, we assist field in regular monitoring of thermal data to optimize the operational parameters, thereby increasing the life of the drum. We also provide enough inspection windows and lanes in our design to inspect critical areas of the drum for early detection of cracks that can be repaired on time to avoid unplanned shutdowns. Therefore, a combined effort is necessary between reliability, process, and operation during the entire life of the drum. At the end of the life cycle, we also assist our clients in coke drum replacement studies. Skirt junction area is one of the prominent locations that experiences frequent cracks due to fatigue. In today's presentation, we will be discussing two case studies that resulted in improved fatigue life of this particular location. First case study discusses about the operational optimization performed in a DCU after startup. And the second case study discusses about online repairs and modification of skirt to improve fatigue life of the drum. Some of the common types of skirt design used in coke drums are tangential lap joint skirt, inline well build-up skirt, and forged wiring skirt. Selection of skirt junction type depends on a lot of factors that includes fatigue life requirements from the client, fabricator's experience, etc. During heating cycle, skirt will be relatively cooler than the drum, therefore it results in restraining the expansion of drum. Similarly, during quench, the skirt will be relatively hotter than the drum and tends to restrain from shrinking back to its original position. As a result, severe bending stress will be induced at the inner crotch area of the skirt. Cracks initiated at this location will become through wall cracks over time and pose stability concern for the skirt. In some cases, these cracks could propagate to pressure boundary and become a huge safety and reliability concern. Therefore, Wood's preferred skirt design option is forged wiring because it removes fabrication-induced stress stressors away from inner crotch area. In 2012, a refiner from Southeast Asia approached Wood to perform design of 4 coke drums. As part of design, forged wiring option was recommended for these coke drums. Finite element analysis was performed to optimize the skirt geometry, and the resulting fatigue life estimate at the inner crotch area was approximately 6,500 cycles. During design phase, there was no actual operating data from field. Therefore, an estimated transient thermal profile was developed based on experience with similar operating units. Later, thermal guidelines were provided to the operator to monitor the severity of gradients and temperature differential during operation. This is the FEA plot showing calculated stresses during design phase. It shows the thermal stresses induced at inner crotch area during coking. And the plot on the right side corresponds to thermal stresses induced during quench. Then total equivalent stress range is calculated using stress tensors, which is approximately 86 KSI. Since forged wiring is shop fabricated with no stress risers, fatigue strength reduction factor of 1 can be used as described in table 5.12 of ASME section 822. And the resulting fatigue life estimate during design phase is approximately 6,500 cycles. In this particular delayed coking unit, one drum had 50 thermocouples installed to monitor temperature data during operation in the areas including shell, cone, bottom spool, and skirt. In other 3 drums, 18 thermocouples were installed only in the shell and skirt. During operation, we reviewed the temperature data collected from all the skin TIs installed in all the 4 drums. For the time being, we will be concentrating only on the TIs installed in the shell portion at elevation close to bottom tangent line, as it directly impacts the fatigue life of the skirt. After startup, we observed severe operation in all 4 drums, and a representative thermal gradient plot collected from one drum is shown here. As you can see, the thermal gradients calculated based on collected data are severe, that is, greater than 10 degrees centigrade per minute, both during cooking and quench. These high gradients will have significant impact on the fatigue life of the skirt. Similarly, the temperature differential in the circumferential direction at this elevation were also higher during water quench. This is primary cause for bulging and cracks induced in the shell courses. Due to the observed severity in operation, we started studying the impact on fatigue life of skirt based on actual TA data collected from the field. The FEA model was reanalyzed and the stresses calculated during cooking are presented here. Similarly, the FEA plot on the right side shows the stresses calculated during water quench. Later, the equivalent stress range was calculated and it is approximately 104 KSI. The observed increase in stress range was approximately 20%, more than the values calculated during design phase. This increase in stresses contributed to approximately 45% reduction in fatigue life estimate at the inner crotch area of skirt junction. Therefore, optimization of process and operational parameters is critical to reduce thermal gradients. The temperature plots in the left side are obtained at the TAs on the shell close to bottom tangent line right after startup. As you can see, the switch temperature, or in other words, the temperature at end of preheating is low, approximately 200 degrees centigrade. This results in increased thermal gradients during cooking. Therefore, operational optimization was performed to increase the preheat duration so that the temperature at end of preheat is increased. As a result of this modification, we were able to increase the temperature at the end of preheat in the range of 260 to 290 degrees centigrade. This helped in reducing the thermal gradients during cooking part of the cycle. The chart shown on the left side corresponds to thermal gradients measured right after startup, which is severe during both cooking and quench. The chart shown on the right side are thermal gradients for the same coke drum after implementing our recommendations. As explained in previous slide, increasing the temperature at end of preheat helped in significantly reducing the thermal gradients during cooking. Similarly, during water quench, flow rate of water was optimized such that lower rate is maintained until the upper end of cone. This helped in reducing the thermal gradients during quench. You can clearly see that after implementing our recommendations, Thermal gradients measured during cooking and quench are less than 10 degrees centigrade per minute. Only occasional peaks were observed during quench, which is greater than 10 degrees centigrade per minute. This chart shows the circumferential temperature differential measured at the shell close to bottom tangent line right after startup. Total of 8 TAs were installed at this elevation, and you can see the delta T measured during water quench was greater than 100 degrees centigrade before optimization. After implementing our recommendations, the delta T reduced and it was less than 100 degrees centigrade. This will help in reducing the rate of bulge formation and cracks at the lower courses of the cell. As explained in few slides back, the plots shown here are FEA results based on thermal transients measured from TAs right after startup. Later, reduced thermal gradients as a result of operational optimization was used as basis and the FEA model was updated. As you can see on the right side, the stresses during both cooking and quench reduced to 56 KSI and 30 KSI respectively. This resulted in fatigue life estimate of 6,200 cycles approximately. This is a significant improvement and the results were close to the initial life predicted during design phase. Therefore, it validates our initial assumptions used during design phase and shows criticality of thermal monitoring and operational optimization to extend the life cycles of coke drum. Now we will be looking at case study 2 where existing solid skirt was modified to slotted skirt. In 2017, one of the refiners from Asia approached Wood to assist in repairing the cracks at the skirt weld and provide recommendation to improve the fatigue life of the skirt junction area. The existing solid skirt was not a wood design and this weld build-up skirt had a thickness of 35 mm. Thicker skirts experience higher thermal stresses during operation and as a result tend to crack faster. The purpose of hot box is to allow for radiative heat transfer between cone and skirt during operation. It helps in heating the skirt during cooking cycle and cooling the skirt during quench cycle, thereby reducing the thermal gradients. The existing hot box was not an optimized design with a length of less than 1 foot. This resulted in higher thermal gradients in the skirt junction area. To make things worse, the drum was operated at shorter cycle. Cracks were observed by field at the inner crotch area of the well buildup within 3.5 to 4 years from startup. Repaired cracks kept resurfacing over time and changing the side feed to dual feed did not help much. This is the transient thermal profile collected from field for 13-hour cooking cycle. This was used as basis for the finite element analysis. The stress results obtained from FEA for existing solid skirt are shown in this slide. The plot on the left side corresponds to stress results during cooking, and the plot on right side corresponds to stress results during quench. The calculated total equivalent stress range for inner crotch area of the well buildup is approximately 167 KSI, and the corresponding fatigue life estimate was 926 cycles. Based on 13-hour cooking cycle, the calculated fatigue life estimate for inner crotch area translates to 2.7 years. The estimate was based on using fatigue strength reduction factor of 1 as shown in table 5.12 from ASME section 8 division 2. Fatigue strength reduction factor of 1 corresponds to ground smooth weld with full volumetric examination and a surface that receives MT, PT and VT examination. Therefore, even with best case scenario for weld, the estimated fatigue life is low. This shows that existing solid skirt was not a fatigue resistant design. Cracks were first observed at this weld somewhere between 3.5 to 4 years from start of operation. That being said, the cracks must have initiated even before that. Therefore, our estimate for the existing solid skirt was really close to the field data, thereby validating our FEA model. As explained earlier, thermal expansion and contraction of drum during operation results in severe bending stresses induced at the inner crotch area. Therefore, cutting slots to the existing skirt will add flexibility to the system, thereby reducing the thermal stresses induced at the inner crotch area. Adding slots and keyholes will result in introducing stress concentrations to the skirt and will become the weakest link. Therefore, cracks will initiate at keyholes, usually at the upper end, before the skirt will build up. Cracks initiated at keyhole are easy to monitor and repair compared to cracks initiated at the skirt weld buildup. And in some cases, the cracks initiated at the skirt weld gets unnoticed and will lead to through-wall cracks, causing stability concern for the skirt. In some cases, they reach pressure boundary, causing huge safety and reliability concern. The design of slotted skirt was performed using FEA, and the key parameters that were optimized includes slot length, number of slots, elevation of slots, keyhole diameter, sequence of slot cutting, etc. Buckling analysis is required in this particular case as there will be reduction in buckling resistance for the slotted skirt. Since ASME Section 8 Division 1 addresses buckling strength only for solid skirt, FEA methodology, load combinations, and minimum requirements per ASME Section 8 Division 2 need to be used to qualify the slotted skirt. The loads used for this analysis includes weight loads during operation, dynamic upset loads, and occasional loads including wind and seismic. Therefore, both transient thermal analysis and buckling analysis need to be performed in parallel to optimize the slot geometry. The resulting optimized design had a fatigue life estimate of approximately 4,200 cycles for inner crotch area and a fatigue life estimate of approximately 3,000 cycles for upper keyholes. Easy to remove insulation window was recommended to inspect and monitor the critical areas that includes keyholes and skirt weld. In this particular case, the client wanted slot cutting to be done on field during operation. Therefore, usual approach of slotted window panel replacement was not carried out. Moreover, during the study, the cycle time was modified to 12-hour coking cycle. Therefore, updated transient thermal profiles collected from the Cogdom TIs were used as basis for this slotted skirt design. For this particular skirt, to achieve considerable improvement in fatigue life, at least 18-inch slot length was required. However, usual approach of locating the slots within the hotbox was not feasible because the existing hotbox length was less than 1 foot. Prior to slot cutting, the crack mapping for entire 360-degree at the skirt weld buildup and knuckle portion of the weld buildup was done. Based on this data, repairs were done using temper bead welding technique to avoid post-weld heat treatment after the repair. The weld hardness was measured to make sure it is within the limits of our specification. A mock-up sample was created to review the quality of the slots before performing actual cutting process. The bottom portion of new slots will extend beneath the hotbox and it results in intersecting with insulation support rings and circumferential weld seams of the skirt. Therefore, inspection of existing circumferential weld seams is necessary prior to slot cutting to make sure there is no cracks in that location. Since the inspection resulted in no cracks, the slot cutting was proceeded without any issues. As explained in previous slide, the bottom portion of slot also intersects with insulation support clips that holds the support ring. Therefore, this additional constraint need to be considered in determining the number of slots required. At last, final number of 108 slots were used such that the center line of slots do not intersect with insulation support clips. At the same time, the slots were located such that they do not intersect the longitudinal weld seams of the skirt. We also specified the sequence of slot cutting when the drum is in cold condition to avoid creating asymmetric weight loads on the skirt. In the end, we provided support to the field and coordinated with the fabricator during the slot cutting process to meet the quality requirements specified for this slotted skirt design. As discussed in these case studies, it is evident that addressing fatigue only during design phase is not adequate. Coordinating with fabricator to meet the design requirements by reviewing fabrication drawings, weld and quality procedures are necessary. After startup, thermal monitoring and operational optimization using our proprietary programs are critical. Providing enough inspection windows to monitor the critical areas of the drum and planning maintenance repairs are important to avoid unplanned shutdowns. In wood, we assist our clients during the entire life cycle of the drum, starting from design phase to replacement of drums at the end of life. Our goal is to provide technical support during different phases of the drum to maximize the coke drum life. With that being said, I will conclude my presentation and please let me know if you have any questions. I will try my best to answer them. Thanks everyone for your time.